Hi, this is going to be a video explaining a more intuitive method for finding the distance between a point and a line. I will be writing down some equations on paper here and methods, but I'll also be illustrating how I'm thinking in the GeoGebra 3D you see on screen as well. So we'll be finding the distance between the point P, which is 1 comma negative 2 comma 3, and the plane, which I'm just going to call pi for now because it's sort of like the Greek P, and we like to use Greek letters whenever we can in mathematics. And this one is given by the equation 2x minus y minus 3z equals 6. And this point and plane are already shown here on GeoGebra on the right. And we want to find the distance now from the point to the plane. So the first thing we want to think about is what it means to find distance between a point and a plane. And I want you to think about if you have, let's say this is the ground, and we have a little airplane flying up here. Airplane with the wings and a little tail here. Bad airplane, but you get the idea. So if we say how high is the airplane above the ground, well, the ground is big, right? We can measure all kinds of places on the ground here, but we don't think of that as the height. We have this intuitive idea that we say straight down. That's what we mean by the height. And what does straight down mean? How do we define that? Well, if we come straight down, we think of it as making a 90-degree angle here to the ground. That's what we mean by straight down. It's also the shortest distance, is the other way to say it, to the ground, but it happens to make a 90-degree angle to the ground. And this idea, this 90-degree angle, right, so we can think of the ground as a plane. And we have this concept of a normal in mathematics, which is 90 degrees to a plane. So now if we go back over here to GeoGebra and we think similarly, like we could think there's lots of lines through this point, right? There's infinite many lines. We think of all the lines that can go through this point. And unless it's parallel to the plane, all of them will intersect the plane somewhere. But they're not all interesting to us, right? We want the one that's going to hit the plane at 90 degrees. That's the one that's going to be interesting to us, right? We're going to want this one, which if we rotate here, I put in a little angle marker there, and we can see it hits the plane at 90 degrees there. So that's the one we want to find. That's the one that's going to be of interest to us. We want to find that particular line through this point, because this will give us the distance we're looking for right here. So now we think about in 3D, how do we make an equation for a line? And if we think about the parametric form of an equation, right, so let's say we have a line L, and the parametric form is going to be a point, and we'll say P, we're going to use P here, but now we're thinking in general, it's going to be a point plus a parameter, which we usually say is T here, times some vector, which is a direction. So what this means is we have a point that's on the line somewhere, and then this is a vector just points in the direction of the line, and then we just scale up this direction vector with t. That'll get us all the points on the line. So the important point to think about, this is a specific point and this is a direction. A specific point on the line and a direction. So if we think about this, if we go back to our diagram here, we have a specific point P, and now we need a direction. What direction is this? Well, the direction is 90 degrees to the plane. But what direction is that? Well, that's the direction of the normal to the plane. The normal to the plane is a direction that is 90 degrees to the plane. And we have a very convenient way of getting that from the equation from a plane. We just take the coefficients of x, y, and z. So in this case, we have x, coefficient of x, coefficient of y minus 1, coefficient z. So if we call the normal vector to the plane n, we know that this is going to be 2, comma, negative 1, comma, negative 3. So that's very easy to read off from the equation of a plane. So we have a normal vector, and this is the direction. We want the line that's through this point, through our point here, through point P here, and in this direction, right? That's the one that's, out of all the different lines I showed you before, that's this line. That's 90 degrees. There's only one of these. But this is very easy, right? Because we have a point and we have a direction now. So the line we want is actually, we rewrite it now as point P, that's our point, plus T, this is just a parameter. But we're going to use n now because we have actually the normal. This is the vector we want, direction. So this equation is for this line here. So great, so now we have the line we want. But what do we actually want to know? We want to know where this line intersects the plane. That's what's interesting because that's the distance we want. So we want to find this point here, which we're going to call Q, where the line intersects the plane. But this is nice. This is simple, basic algebra. How do we find the intersection? And you can think back to 2D geometry. If I have the equation for two lines in a plane, it's a system of equations, right? You just have a system of equations and you solve them for a variable. To understand how to do that here, so here are two equations and we want to solve this, but what can we solve for? It seems like in some sense we have too many variables. We have x, we have y, we have z, and we have t. So we only have two equations. So we want to reduce this, reduce the number of variables somehow. And it turns out this is going to be really simple to do, and we're going to end up solving for t, which is going to be quite convenient. So what we're going to do is we're going to change the way we write this line. I'm going to expand out to write the point and the vector out. So here we have the point is 1, comma, minus 2, comma, 3, plus t times the normal vector is 2, comma, minus 1, comma, minus 3. And now we're going to think of the equation for every point in the line. We're going to combine the parameter form. This is one nice way to write it. We have a point plus t times a vector. But we can combine this into just an x-coordinate, a y-coordinate, and a z-coordinate. So what is the x-coordinate for every point in the line? It's going to be, using this equation, it's going to be 1 plus t times 2. So let's write that as its own point here. 1, that's just 1 here, plus t times 2, right? The x-coordinate plus the scaled up version of it, plus t times 2 we'll write as 2t. What's the y-coordinate? It's going to be minus 2 plus t times minus 1. Minus 2, well, t times minus 1 is minus t, so minus t. And of course the z-coordinate is going to be 3 plus t times minus 3. So 3 plus t times minus 3 is minus 3t. So this is the same as this. It's the equation of a line, but now I've sort of combined this form into writing the parameter as each coordinate instead. The only reason I've done that is to make it easier to see the next step. So where these two intersect, that means they have the same x, the same y, and the same z. That means that the x here must be the same as the x here. The y here must be the same as the y here, and the z here must be the same as the z here. That's what it means to intersect. The point has the same x, y, z coordinates in both equations. Well, that's very convenient now. If these are going to be the same, x is the same here and x is the same here, that means I can put this into the x here, and I can put this into the y here, and I can put this into the z here. And then I'm going to only have one variable. So let us do that. So I'm going to take 2 times x, so this, I'm going to put this in here. So that's 2 times, I put that in instead of x, 1 plus 2t. And then I'm going to have minus, and I'm going to put this in parentheses. We just have to be very careful with the minus signs. So instead of y, I'm going to put this whole thing here, minus 2 minus t. And then here we have minus 3, and then in parentheses, instead of z, I'm going to put this here. 3 minus 3t, and this whole thing is equal to 6. And now it's great. I only have, this is basic algebra. I have one variable, one equation. I can just solve for t. So we'll just do that rather quickly here. Multiply out the parentheses. 2 plus 4t. Be careful of the minus signs here. So this will be plus 2 plus t. This will be minus 9 plus 9t. Being careful about the minus signs again. So if I combine the t's, I have 4, 5, and 9. So that's going to be 14. So it's going to give me 14t. And the other ones I have 2 plus 2 minus 9. So that's 4 minus 9 is minus 5 equals 6. So then I can rewrite that, of course, as 14t equals 11. So we have t equals 11 over 14. So now we have our t value, and that gives us the intersection point. So what does that mean? That means that it's a point on this line with this t value is another point. So we could say that point Q equals, it's going to be point P plus, and this is a t value, 11 over 14 times n. And this will give us a specific point now. When we just use t, it's all points, but we have a specific t value for this specific point. And we can leave it like that for now. We could write it out, right? We could multiply this out. We can multiply all the n values here by 11 over 14 and add them to the p values, and then we could get just 3 numbers, an x, y, and z coordinate here. It turns out it's going to be way more convenient for us to leave this form. And it's nice when you're able to like see these kind of shortcuts and don't do unnecessary calculations. And you'll soon see why it's much better to not calculate the actual values of that point. We don't actually care about the actual values at the point. What we care about is the distance. So if we look over here again at GeoGebra, what we actually care about is now that we found Q, we want to find that distance there, the distance between P and Q. So there's many different ways to do that. A convenient way is, for example, if we think of a vector from, let's say, from P to Q, right? So if we think of this as a vector from P to Q, and the normal way to do that would be to take the point, right? We take the point Q minus the point P, right? That's how we would calculate a vector between 2 points. And then once we have that vector, we can calculate the size of that vector. And the reason this is convenient is if we watch what happens here, right? So Q, this is Q. So Q is P plus 11 over 14n. And then we take minus P. But look at that. The P minus P's disappear. And this is just 11 over 14n. So that's quite convenient. We didn't need to do any other calculations because the p's disappear. And all that actually mattered was the t value and the normal vector. So that was all we actually needed here. So we want the size of this. We would like the size of PQ, the magnitude or the absolute value, depending what you want to call it, but it's the length of this vector. And you can use the standard formulas for this. If you're not familiar with how it works, you could multiply out the 11/14th and then calculate it. But it turns out when you have a constant multiplied by a vector, that you could just put that in front of the calculation. You won't. That's going to be the same. And then it's going to be the magnitude of n. And you can verify this yourself to see that it works. It's very convenient. We don't have to multiply all the values of n by 11/14th and then do the formula. We could just simply take out the 11/14 is going to be the same. And you'll see that if you try it. And so it makes the calculation much, much easier, 11/14. So we have the formula for the length of the vector, and of course that's the square root of the x-coordinate squared. So that's going to be 2 squared plus the y-coordinate squared, so that'll be minus 1 squared, plus the z-coordinate squared, minus 3 squared. And of course, this is a much easier calculation to do than if we had multiplied each of these by 11/14, squared them, and then taken the square root. That would be much messier. This is, of course, much simpler. So it's nice that that works out. So it's 11/14 times the square root of, so it's going to be 4 plus 1 plus 9, which of course equals 11/14 times the square root of 14. And there's a simpler way to write this. This is possibly okay, but if we remember that 14 equals the square root of 14 times the square root of 14, of course, then we can possibly, depending again on your perspective. Some people like to write it like this. Sometimes you'll see it written like this, 11 over the square root of 14. And this is because this 14 is square root of 14 times the square root of 14. So this cancels as one of those. You can förkorta. You could reduce with the square root of 14. And you're left with 11 over the square root of 14. So your answer is either 11/14 times the square root of 14 or 11 over the square root of 14. So that is the distance between a point and a plane.